Welcome back to Triple 101. Today we will talk about capacitors and inductors. You have been introduced to capacitors in college. A capacitor essentially consists of two parallel metal plates separated by an insulator, which we call a dielectric. If we apply a voltage across the two plates of the capacitor, a positive charge is accumulated on the metal plate which is connected to the positive polarity of the voltage. An equal amount of negative charge is accumulated on the plate which is connected to the negative polarity of the voltage. A fundamental property that a capacitance have is that this charge is proportional to the voltage. We can eliminate the proportionality sign by introducing a constant of proportionality, and we can write Q is equal to CV. This proportionality constant C is called the capacitance of this structure, and the unit of capacitance is farad. In an electrical circuit, we are more interested in the relationship between the current and voltage. We recall that the current is the time derivative of charge. So using I equal to dq dt, the Q equal to CV equation can be recast in the form I is equal to C dV dt. This is called the IV relationship for a capacitance. The circuit symbol of a capacitance in an electrical circuit is given by this symbol, and note here that the current and the voltage of this equation satisfy passive sign convention. To obtain the relationship between voltage and current, that is the VI relationship, we integrate the IV relationship, this one, from an initial time t0 to the present time t. If we integrate both sides from t0 to t, we get this equation. Vt is the voltage at time t, which we want to find out. Vt naught is the voltage across the capacitance at an earlier time t naught. This t naught time is called the initial time, and Vt naught is called the initial value. In the integration, t is replaced by t prime because this is a definite integral, and t prime is the dummy variable of integration. The time t is the upper limit of the integral. We can now calculate the power of the capacitance using P equal to VI. This gives us this relationship, and we call this the power relationship. If we integrate power, we get energy. The capacitance, unlike a resistance, does not dissipate the energy it absorbs. The resistance dissipates the energy in the form of heat or light, but the capacitance stores the energy in the form of voltage or electric field in the dielectric. It is possible to recover the stored energy from the capacitance at a later time. So for a given voltage across the capacitance, how much energy is stored in the capacitance? We can find it by integrating the power. Energy is integral of power. So at time t, the energy stored in the capacitance is equal to 1/2 CV square, where V is the voltage. This is also a very important relationship for a capacitance. Now we discuss two important properties of capacitance. First, let us consider DC circuit. In a DC circuit, the voltages and currents are all constant. They do not change with time. So the time derivative of the voltage is 0. Because the capacitance current is equal to C dV dt, if dV dt is 0, the capacitance current is also 0 under DC condition. If the current through a circuit element is 0, that circuit element behaves as an open circuit. So we can argue that the capacitance behaves as an open circuit in DC. In the next property, we state that the voltage across a capacitance as a function of time cannot have any discontinuity. The capacitor voltage cannot change abruptly or instantaneously. What does this statement actually mean? To understand that, we look at two voltage functions as a function of time. We want to look at the values of the voltage V1 and V2 when the time is t naught. If we look at the value of V1 at time t naught, we see that if we approach t naught time from the left, or if we approach t naught time from the right, for V1 at t equal to t naught, we get the same value. So the equation that we write is this: t naught minus represents the value of V1 at time t naught when we approach from the left. V1 t naught plus represents the value of V1 at time t naught when we approach from the right. For V1, these two values are equal, and this implies that V1 voltage is continuous at time t naught. There is no discontinuity. However, if we look at V2, when approaching from the left, the value that we get is this. We call it V2 T naught minus. When approaching from the right, we get this value, V2 T naught plus. And it is clearly seen that V2 T naught minus and V2 T naught plus are not equal. If they are not equal, we say that the voltage V2 has a discontinuity at t equal to t naught. This t naught minus and t naught plus can also be viewed as times where t naught minus is just to the left of t naught and t naught plus is just to the right of t naught. If the voltage values at these two times are different, there is a discontinuity in the voltage at that time. The second property states that the capacitance voltage cannot have such discontinuities. So this V2 is not an acceptable voltage for a capacitor, whereas V1 is an acceptable voltage. The condition of statement 2 can be mathematically expressed in this way. If we choose any time t naught, the value of the capacitance voltage just to the left of t naught and the value just to the right of t naught are always equal, implying that the capacitance voltage does not have any discontinuity at any time. Okay. Uh, we have already mentioned that the capacitance stores the energy it absorbs. And it is possible to extract the stored energy from the capacitance and let the capacitance supply electrical energy at a later time. However, the amount of energy that the capacitor can supply is only equal to the amount what was initially stored in the capacitor. C cannot generate any electrical energy, unlike a generator. For this reason, even though the capacitance can supply energy, it is not called a source. Rather, it is considered as a passive element like a resistance. If we consider the storage and supply of energy in electrical form, the capacitance behavior is somewhat similar to the behavior of a rechargeable battery. Both stores energy and supplies energy. However, a battery and a capacitance are not the same. The battery stores the energy in chemical form, whereas the capacitor stores the energy in the form of voltage or electric field. In electrical engineering, capacitors are widely used as energy storage elements. Now let's look at a simple problem. We have a 5 farad capacitance whose voltage is given by this equation. We want to determine the capacitance current. We also want to find out the energy which is stored in the capacitor at 0.25 seconds. Voltage is given, we want to find the current, so we use I equal to C dV/dt relationship. If the capacitance is in farad, the voltage is in volts, and time is in seconds, the unit of current will be in ampere. Using the product rule, we can differentiate this function easily, and finally we get that this is the current flowing through the capacitor corresponding to this voltage. Now to find the energy at 0.25 seconds, we need the voltage at 0.25 seconds. To calculate that, we simply put t equal to 0.5 seconds in this equation. That gives us at 2.5 seconds, the capacitance voltage is 0.236 volts, and the energy stored in the capacitance at that time is equal to 0.139 joules. Okay, so this ends our discussion as on the basic properties of capacitance in an electrical circuit. Now let's talk about inductors. Inductor or an inductance is the property and inductor is the name of the circuit element. An inductor is a coil of a conducting wire around a core material. The core material is typically magnetic, but it can also be non-magnetic, such as the air. In this structure, we have n turns of the wire around the core, and the length of the coil is L, and the cross-sectional area of the core is A. If a current flows through this coil, a magnetic flux will be produced in the core, whose direction we can find out using the thumb rule. This magnetic flux, which is produced by the current by observation, is proportional to the current. Phi is proportional to the current. This is one of the most important properties of the inductor. We can get rid of the proportionality sign by introducing a proportionality constant, and we can write this equation. Instead of phi, I write n phi here, and n phi is equal to excuse me, n phi is equal to Li, where L, the proportionality constant, is called inductance, whose unit is Henry. In an electrical circuit, we are more interested in the relationship between voltage and current. For that, we recall Faraday's law, which relates the voltage with the time derivative of magnetic flux. Differentiating both sides of this equation, we obtain V is equal to L di dt. We call this relationship VI relationship. The circuit symbol of an inductance is given here. Again, we see that the voltage and the current of this relationship satisfy passive sign convention. Okay, now to find the other relationship of the inductor, such as IV relationship, power relationship, energy relationship, we can take two different approaches. We can derive each relationship going through the mathematical processes as we did for the capacitor, or we can do mapping. Let's apply the mapping technique because it is quite interesting. This is the IV relationship of the capacitance, and this one is the VI relationship of the inductance. If we look at the mathematical structure of these two equations, these are identical. Both are of the form of y equal to k dx dt. Here y and x are functions of time and k is a constant. Okay, so how do we map y equal to k dx dt for the capacitance or for the inductance? By using this table. For a capacitance, K is equal to C, Y is equal to I, X is equal to V. For an inductance, K is L, Y is V, and X is I. So if we take all the equations of the capacitors, and in every equation, if we replace C by L, V by I, and I by V, we will get the corresponding equations for the inductors. It is not necessary to derive these equations independently again. Okay, so if we do that thing, these are the equations we get for the inductor. The right column are the equations for the inductor, which have been obtained by mapping the corresponding equations of the capacitor given in the left column. The first one is the VI relationship, the second one is the IV relationship, the third one is the power relationship, and the last one is the energy relationship. Okay, we now talk about the two important properties for inductance. Remember, we already know about the important properties of capacitance. In DC, a capacitance was behaving as an open circuit because the current through the capacitance was zero. If we look at the inductance using the mapping, we can argue that the voltage across the capacitance is, the voltage across the inductance is zero, and the inductance behaves as a short circuit. So in DC, the inductance behaves as a short circuit, which is the first property. In the second property of the capacitance, we discussed that the capacitance voltage cannot have any discontinuity. This is a continuous function of time. For inductance, using the mapping, we say that the current through the inductance cannot have any discontinuity. The inductor current is a continuous function of time. That implies that at any time t0, the inductor current just before t0, which is t0 minus, is equal to the inductor current just after t0, which is t0 plus. And this relationship holds for all possible values of t0. We show here two graphical representations of current. In the figure A, the current is a continuous function of time. There is no discontinuity. So this type of current is allowed through an inductor. But in graph B, the current has two discontinuities. This is a discontinuity and there is another discontinuity. So this cannot be the current through an inductance. Okay? Again, if we look at the energy situation of an inductor, the inductor does not dissipate any energy it absorbs. In this respect, the inductor behaves similar to the capacitance. But the difference is the capacitance stores the energy in electric field and the inductor stores the energy in the magnetic field of the core. It is possible to extract the energy, stored energy, from the inductor at a later time when the inductor will be supplying electrical energy. But the amount of energy that the inductor can supply is only equal to the amount which was initially stored in the inductor. That means the inductor cannot generate any electrical energy. For this reason, again, like capacitance, L is not considered as a source, rather it is considered as a passive element. Inductors are also widely used in electrical circuits as energy storage elements. In addition to the energy storage property of the inductance, it has another interesting property. The inductance has its tendency to oppose any change of current. If the current wants to change rapidly, the inductor develops a voltage across it and opposes the current. The ballast or the choke coil in a conventional tube light is an example of use of this property of the inductance. Okay, now we look at another problem. The voltage across a 2 Henry inductor is given by this relationship. We want to find the inductor current. We also want to calculate the amount of energy that is stored in the inductor. It is mistyped here, in the inductor at t equal to 0.25 seconds. I think there is some typographic error. This sentence should not be there. We want to find out the energy stored in the inductor at t equal to 4 seconds. Let's ignore this sentence. And in addition to the question, another information is given that at t equal to 0, the current flowing through the inductor is 2 ampere. The voltage is given. We want to find out the current. We need the IV relationship. This is the IV relationship where we require an integration from T naught to T, and the value of the current at T naught needs to be known. The question is, what is T equal to? If we look at the equation, the T naught is such a time when the inductor current is known. From the question, we know the inductor current at t equal to 0. So T naught is 0 and IT naught is equal to 2 ampere. So we can formulate this integral in this way. L is 2 Henry. The integration limit is from 0 to t. The voltage as a function of t prime is shown here, and we have the initial value. And after the integration, we get this expression for the inductor current. Next, we want to find out the energy stored in the inductor at t equal to 4 seconds. So I need the inductor current at t equal to 4 seconds. For that, I put t equal to 4 seconds in this equation, and the result turns out to be minus 18 ampere. So W4 is 1/2 Li square, where I is minus 18 ampere. If we do the calculations, we get that at 4 seconds, the energy stored is equal to 324 joule. That's all in this lecture. Thank you.